Every AI model you use is frozen. The moment training ends, the weights lock. ChatGPT, Claude, Gemini. Billions of parameters sealed shut. They process your questions, but they don't learn a single thing from them. Think about that. You could explain your entire code base to a model, walk it through your company's architecture, teach it your preferences over months of daily conversation. Come back the next day, and it starts completely from scratch. All that context, all those explanations gone. Not one weight changed. Not one connection rewired. The industry's answer? Bigger context windows. 1 million tokens. 10 million. But a bigger window isn't memory. It's reading a longer book without being able to take notes. More input, zero learning. In January 2025, a team at Google Research asked a different question. What if an AI could learn the way humans do? Not by processing everything equally, but by paying attention to what surprises it and letting go of what doesn't. They called their architecture Titans, and a model with 760 million parameters used it to beat GPT-4. Here's a quick experiment. What did you eat for lunch 3 Tuesdays ago? No idea, right? But if a stranger had walked up and flipped your table, you'd remember everything. The food, the restaurant, the exact moment it happened. Routine gets discarded. Surprise gets locked in. That's not a bug in human memory. It's the entire design. Psychologists call this flashbulb memory. Your brain runs a constant prediction engine. Every moment, it's generating expectations about what happens next. When reality matches those expectations, the information passes through and fades. Not worth storing. But when reality violates the prediction, your brain flags it, encodes it, locks it in. The prediction error becomes the learning signal. You don't run on one memory system, you run on 3. Short-term handles what you're actively thinking about right now. Fast, but it holds maybe 7 items at once. Long-term stores experiences over years, constantly rewritten by new events. And then there's a deeper layer for things so embedded you never consciously think about them. Your native language, how to ride a bike, your own name. 3 systems, 3 speeds, 3 purposes. That split turns out to be everything. What if a neural network could grow another neural network inside itself? That's literally what Titans does. The outer model trains normally. Months of compute, billions of examples. Once training ends, it freezes like everything else. But nested inside it is a smaller network, a memory module. And this one doesn't freeze. While you use the model, while it reads your input, this inner network is rewriting its own parameters in real time, token by token. During training, the outer model learns the rules for that inner network, what to keep, what to forget, how aggressive the updates should be, but those rules sit dormant until you actually use the model. The moment inference begins, the memory module wakes up. Every token it reads triggers a live weight update. It's learning in real time, following rules it was trained to obey. Now here's where it maps back to the brain. The full Titans architecture runs 3 parallel systems, just like the 3 memory types in your head. Attention handles the current window. That's short term. Persistent parameters store general knowledge baked in at training. That's the bedrock. And the neural memory module sits alongside both, updating its weights live. In one configuration, memory retrieves first. Then attention picks the winners. Here's the part that makes the whole thing work. It's not what Titans remembers. It's what it gets wrong. A token arrives. The memory module creates a key from that input and queries its own weights. Have I stored anything useful about this before? If the recall closely matches what's actually needed, the error is small. Low surprise. Memory doesn't bother updating. That token wasn't worth learning from. But when the prediction is dead wrong, when the memory has never seen anything like this input, the error explodes. High surprise. And here's the key insight. Titans takes the gradient of that prediction error, the mathematical direction of steepest change, and fires it backward through the memory's weights. Gradient descent, the exact same process that trains neural networks over weeks, now running live. During inference, large error means large gradient means large update. The model rewrites itself hardest at the exact moments it's most confused. Not the easy predictions, not the routine, the things that break the model's expectations. That's where the learning happens. And surprise doesn't vanish after one token. Titans adds momentum. One surprising moment carries its influence forward through the sequence, giving the tokens that follow extra weight in memory too, like how a shocking event burns every surrounding detail into your brain, where you were sitting, what song was playing, that flashbulb effect from the restaurant, now encoded in math. A single moment of confusion amplifies everything around it. But here's what surprised even the researchers. They removed each component to see which one the system needed most. Not the momentum. Forgetting. An adaptive decay that purges old, irrelevant memories to make room for new ones. Without it, the memory fills with noise and performance collapses. You literally can't learn if you can't let go. Now for the part that shouldn't be possible. A Titans model with 760 million parameters was pitted against GPT-4 on the Babylong benchmark, a test for multi-hop reasoning over extremely long documents. Also in the ring, Llama 3.1 at 70 billion and recurrent Gemma at 9 billion. Models 10 to 2,000 times its size. Titans won, decisively. On the needle in a haystack test, finding one specific piece of information buried deep in thousands of tokens, Titans scored 98.4% on passkeys and 97.4% on numbers. Mamba 2, one of the best linear models, 5.4% on passkeys and 0 on numbers. It couldn't find a single one. On standard language modeling, predicting the next word, Titans hit a perplexity of 18.61. The previous best, gated DeltaNet, 21. Standard transformers, 25. Lower is better, that's not a marginal gap. And the team proved mathematically that Titans can solve a class of problems that transformers literally cannot. Not just faster or more efficient. The architecture is theoretically more expressive. And here's what kills every other long context approach. Standard attention chokes because every token has to compare against every other token. Quadratic cost, double the input, quadruple the compute. Titans compresses history directly into its weights instead of holding every token in the window. It handles over 2 million tokens and the cost barely moves. Every conversation you've ever had with an AI has been a one-way street. You give it input, it processes, it responds. But the model itself doesn't budge. Nothing is retained. Nothing is learned. The next conversation starts from zero, like meeting a stranger every single time. Titans changes that equation. The model starts adapting to your input the moment the first token arrives. It's rewriting itself while you talk. And Google isn't alone in this direction. DeepSeek is building conditional memory into their next model. Mamba 3 is pushing state-space models forward at ICLR 2026. The whole field is converging on the same realization. The next leap in AI isn't a bigger brain. It's a brain that actually forms memories. For years, the entire industry has been focused on one goal: minimize errors. Get the right answer. Reduce mistakes. Titans flips that completely. The errors are the signal. The confusion is the curriculum. The moments where the model is most wrong are exactly the moments where it learns the most. Most architectures throw prediction errors away after training. Titans uses them in real time to build live memories. Turns out confusion was the breakthrough all along.